Welcome back to the Foundry by Forge College. Let's jump right in. Today's explainer is all about the role and importance of turbine and Solana data transfer. If you've been following along with our Web3 journey, you already know we absolutely love popping the hood on these massive engines. So today, we're taking a really close look at Solana's data delivery, and we're going to figure out how it moves information across the globe faster than you can blink, all without crashing the whole system. Here's our engineering blueprint for today. We've got Welcome to Turbine Protocol, 2. Architecture versus delivery, 3. The postal hub model, 4. Tracing a packet's journey, 5. Measuring and tuning performance, and 6. Preparing for data sharding. Let's get going.
Section 1. Welcome to Turbine Protocol. Let's do a really quick recap. Okay, so last time we learned that Turbine uses this tree-based fanout to push data. Instead of a leader node just screaming the entire block out to every single node on the network, which would be total chaos, it passes pieces to a few neighbors, who then pass it to their neighbors. But to truly grasp the sheer speed of this process, you need to look at this equation. Solana's data transfer equals architecture plus delivery. The speed we actually care about is the product of these two very distinct layers working together. Moving on to Section 2. Architecture versus delivery. So if you're out there running a validator, you really need to know exactly which levers to pull, right? Well, think of architecture as your physical map. It covers network topology, relay duties, and hop counts. Essentially, it dictates who connects to whom. Delivery, on the other hand, is basically the rules of the road. We're talking chunking rules, scheduling, and retransmissions. To put it simply, architecture constrains the fanout, while delivery slices up the payload to make that constrained fanout incredibly efficient. Section 3, the postal hub model. Let's use a bit of an analogy here. Imagine a central printing press trying to shove 1 million heavy Sunday newspapers into one tiny delivery van and driving to every single house. The van would literally explode, the roads would gridlock, and you'd probably get your Sunday paper on a Thursday, right? Instead, what do? They send massive pallets to regional hubs, which then pass them down to local post offices. It totally prevents a traffic apocalypse. And that, in a nutshell, is the postal distribution model. We can map this directly to Turbine. Our leader node, that's the central printer. The fanout relays act as those regional sorting hubs, and the leaf validators are the individual households. And chunking? Well, that's like ripping the newspaper apart so one van takes the sports section, another takes the comics, and they all get reassembled flawlessly right at your doorstep. Of course, in the real world, things do go wrong. A mail carrier drops a paper in a puddle, or a road gets congested. In the blockchain world, a network suffers from bandwidth saturation, packet loss, or node churn. But here's the thing. If a paper gets ruined, you don't call the main printer 1,000 miles away, do you? No, the local hub just sends a replacement. Turbine does the exact same thing. It uses localized retries from a nearby relay to save precious global bandwidth.
All right, Section 4, tracing a packet's journey.
Let's put all this into practice and trace a packet's actual life cycle. Step 1, block creation and slicing. The leader packs the boxes, slicing the block into addressable chunks. Step 2, fanout assignment. It consults the map and fans those chunks out to its immediate relays. Step 3, parallel forwarding. These relays toss the chunks down the branches concurrently, which vastly reduces delivery times. Step 4 is local reassembly. Validators catch all those chunks and piece the paper back together. Step 5, retransmit scheduling. If a piece is missing, the validator quickly asks a neighbor for just that specific piece. And finally, Step 6, block finalization, where the validator verifies the fully assembled block. This whole parallel process limits global bandwidth waste while keeping latency ridiculously low. It's pretty amazing.
Section 5. Measuring and tuning performance.
Now, this beautifully engineered system really only works if we know how to monitor it. Consider this your ultimate troubleshooting cheat sheet. Every component has a direct operational impact. For instance, the leader controls latency and upstream bandwidth. If you tighten the fanout relays too much, you spike your CPU load. Chunking enables parallelism, sure, but it also increases your bookkeeping. And that retransmit scheduler, it prioritizes those missing pieces, shaping resilience to packet loss. When you know the component, you know exactly which lever to pull when the network alarms start blaring. So when you're checking your dashboards, you want to watch 3 things very closely. Spiking per hop bandwidth, you've got network hotspots, and you need to adjust your physical map. What about slow reassembly times? Well, that points to bad scheduling, meaning your pieces are probably arriving out of order. And a high retransmit frequency basically means poor link quality. These metrics are absolutely crucial. They tell you exactly whether you need to fix your architecture or tweak your delivery rules. Moving to our final section, Section 6, preparing for data sharding. Once you fully understand this baseline, you can really start optimizing. There's a golden rule here. Tuning chunk order or retransmit behavior can often fix latency problems without altering the fan-out tree. Think about that for a second. Sometimes you don't need to spend millions rebuilding the digital highways. You just need to pack the delivery vans a bit smarter. Adjusting your delivery rules is often a much, much faster fix than completely re-architecting your topology. But as we look to the future of network scaling, I want to pose a bit of a provocative question to you. Even in this highly optimized, brilliantly scheduled postal network, what happens when multiple validators repeatedly request the exact same missing chunks over and over again? It reveals a major inefficiency that still exists. I mean, if everyone in a neighborhood keeps missing the finance section of the newspaper, having the local hub individually resend it 20 times is still a massive waste of resources, isn't it? That lingering redundancy is exactly what we'll be tackling next when we dive into the principles of data sharding. Well, that wraps it up for today. Thank you so much for joining me for this explainer created by Forge College. Be sure to head over to forge.college to learn more about this subject, explore our advanced courses, and dive even deeper into Web3. Keep learning, keep building, and I'll see you in the next one.